Okay, so I'm going to go through the PowerPoint on complex numbers day one, and some of this stuff hopefully you already read in class today, so I'm going to go a little quickly through the first few slides here. So we're talking about graphing complex numbers in the complex, or what IB calls the Argand plane. And the biggest thing to remember is that we graph these similar to how we would graph vectors, but that your x-axis is your real axis, and your y-axis is your imaginary axis. For example, the vector 2, 3 would be the complex number 2 plus 3i. Vector 4, negative 1 here would be the complex number 4 minus I. The vector 0, negative 4 would just be the complex number negative 4i, so notice that's on the imaginary axis. And then the vector negative 3, negative 1 corresponds to the vector negative 3 minus I. Okay, so if we were asked to add two vectors together, or two complex numbers together, algebraically and vectorially or graphically, algebraically it's real simple. You did this in Algebra 2. You just add the two numbers together by combining like terms. But graphically, here's what this would look like. So we have the function, or the complex number 3 plus I. Notice it's in the first quadrant. We do the tail to tip method just like we did with vectors. So at the end of that, we would put 1 minus 4i. And the resultant vector would be the sum of v1 plus v2. And you notice that's 4 minus 3i. 4 units in the real direction, negative 3 units in the imaginary direction. Track these two vectors. Again, we just combine like terms. If I want to do z1 minus z2, here's z1. Negative z2 would just go in the opposite direction. Here's the result. And notice that's 2 in the real, 5 in the imaginary direction. Okay, complex conjugate. So this is a term you should have learned in Algebra 2. I'm just going to remind you what it is. If we have the imaginary number x plus iy, the notation that IB uses is z star, and that would correspond to x minus iy. The modulus of a complex number, and the notation for it looks like absolute value, but it's really just the magnitude of the vector. The same way we calculated magnitude in the last unit, we're going to calculate the modulus for the number in this unit. Some important properties of the modulus that you're going to need to remember. The magnitude of z star would be the same as the magnitude of the modulus of z. The modulus of z squared could also be expressed as z times z star. If you have two complex numbers which are multiplying together, the modulus of their product is just the modulus of each one multiplied together. Same thing with division, and that can be extended as many times as we need to. Okay, so z1 minus z2, that absolute value or modulus, that's the distance between points p1 and p2. Let's look at a quick example. Suppose p is at 2, 3 and q is at 6, 1. And those are 2 points on the Cartesian plane. Use complex numbers to find the distance from p to q. What they're asking to do here is let z1 be the 2 plus 3i to correspond with p, and let z2 be the number 6 plus I. One way we could calculate the distance from p to q is just to do the modulus of z1 minus z2. That's z1 minus z2, so if we calculate the modulus, we get square root of 20. For the midpoint, we're just going to average z1 and z2 together. So we have 2 plus 3i plus 6 plus I. So if we divide each of those by 2, we get 4 plus 2i. So the midpoint of that segment from p to q would be 4, 2. It's just another way of calculating distance and midpoint, but using complex numbers to do it. Okay, so this next section is new, but it ties into some of what we did in the last semester when we talked about polar. We're going to use a lot of polar, actually, when we work with these problems. So let's suppose we've got a complex number that stops at point xy, and it's in the first quadrant the way I've drawn it. The complex number z equals x plus iy the angle theta that z makes with the positive real axis. So in other words, the positive x-axis, that's called the argument of z, and the notation for it is arg z. Think about real numbers. The argument for a real number, meaning it would be on the x-axis somewhere, would have to be either 0 if it's on the positive x-axis, or pi if it's on the negative x-axis. If it's a strictly imaginary number, it would have to be on the y-axis somewhere. So the argument would either be pi over 2 or negative pi over 2, or 3 pi over 2. There's a lot of answers you can have for some of these arguments because of the periodic nature of the circle. One thing we're going to spend some time in this unit, when we get into solving equations, we're going to really need this, is to convert a complex number from Cartesian form into polar form. This x plus iy that we've been dealing with, that's the Cartesian form of a complex number. So to convert it to polar form, we're going to use these two rules. Remember that x is our cosine theta, y is our sine theta. If that's the case, then z could be expressed as x plus iy, or r plus r cosine theta, plus I times r sine theta. If we factor the r out, this is what I call cis form of the number, cis form of the complex number, where the r stands for the modulus of z. And we can sometimes write cosine theta plus I sine theta as cis theta. And a lot of times I use that notation. Hopefully this looks a little bit familiar to you. This is something you would have done at the very end of pre-calculus when you worked with something called De Moivre's theorem, which we're going to talk about tomorrow. Here's kind of the summary of this plot. Any complex number z that's in Cartesian form, x plus iy, can be written in polar form of magnitude of z, or the modulus of z, times cis theta, where theta is the argument. And of course, that absolute value of z notation is just the modulus of z. You can write it as r like we did up here. We can use the modulus notation. Let's do an example. Write in polar form. So we have 2i. Remember, this is the polar form of the number. We need to start by finding the modulus. The modulus for 2i is 2. And that should kind of make sense to you. Now think about where 2i is. That would end up on the positive side of the imaginary axis. So the argument for that would be pi over 2. So in polar form, we would express this as 2 cis pi over 2. Okay, negative 3, that would be on the negative side of the real axis. Modulus, of course, would just be 3. The argument would be pi. So in polar form, we'd write this as 3 cis of pi. One minus I. So think about what quadrant that would be in. Let's start with the modulus. That would be the square root of 1 squared plus 1 squared, or square root of 2. If we were to sketch this, it would be in the fourth quadrant. And the argument for this would be negative pi over 4. Think about how we could get that. We could use tangent to get that. Tan theta, opposite over adjacent. So 1 over negative 1. In the fourth quadrant, that'd be negative pi over 4. You could also use 7 pi over 4 if you went the other way around the circle. That would be a valid answer. But our polar form here is radical 2 cis of negative pi over 4 or 7 pi over 4, whichever one you prefer. And going back in the other direction is pretty simple. So this is in polar form. We want to convert it back to Cartesian. All we're doing is going to expand that cis and write it as cosine 5 pi over 6 plus I times the sine of 5 pi over 6. And just replace those with the appropriate unit circle values. So we have negative root 3 over 2 and 1/2. Then just distribute the square root of 3. There's your Cartesian form, the x plus iy form. Okay, so one last thing I want to talk about in this PowerPoint is why we want to work with numbers in polar form, complex numbers in polar form instead of Cartesian. And the reason is it sometimes makes it easier to multiply and divide them. So a couple of properties here that you need to make sure you know. If I have cis of theta times cis of phi, we can express as a cis of theta plus phi. Cis of theta divided by cis of phi, we could express as cis of theta minus phi. And then cis of theta plus 2k pi, we can express as cis of theta. These first two, I kind of like to think about as they're similar to log properties and rules we have in logarithms. There's a way you can remember those. So a couple quick examples here. Cis of pi over 5 times cis of 3 pi over 10. What that property says is we can put those together and make it cis of pi over 5 plus 3 pi over 10. Really pi over 2, cis of pi over 2. And if we put the answer back in Cartesian form, by expanding it, we just get I. Cis of pi over 5 over cis of 7 pi over 10. We can write as cis of the difference between those two, cis of negative pi over 2. And then expanding that back into Cartesian form, we get negative I. Okay, here's an example. We have cis of 107 pi over 6. So we're going to use that third property that was on that last PowerPoint or last slide with the properties. So 107 pi over 6 can be expressed as 17 and 5 pi over 6. Do some long division, or you'll see it. Since that can be written as 18 pi minus pi over 6, that puts me into the fourth quadrant here. Well, that property said that cis of theta plus 2k pi is just equal to cis of theta. So if we drop that 18 pi, we're left with cis of negative pi over 6. And then expanding that, we get this in Cartesian form. Okay, last problem. So use complex number methods to write cosine of 7 pi over 12 and sine of 7 pi over 12 in simplest surd form. It's an IB term that just means simplest radical form. So what we're going to do is we're going to write this as cosine of 7 pi over 12 plus I sine of 7 pi over 12. Of course, is cis of 7 pi over 12. 7 pi over 12 can be expressed as 3 pi over 12 plus 4 pi over 12. And those, of course, are unit circle values. Well, using our new properties, that can be written as cis of pi over 4 times cis of pi over 3. So if we go back to Cartesian form and multiply all this out, you see where everything's coming from. Cis of pi over 4 becomes radical 2 over 2 plus radical 2 over 2 times I. Cis of pi over 3, that'd be cosine of pi over 3, which is 1/2, plus sine of pi over 3, root 3 over 2 times I. Multiplying all that out, we get this. And if you'll notice, I grouped the real terms and I grouped the imaginary terms. So remember what this expression was equal to. We started out with cosine of 7 pi over 12 plus I sine of 7 pi over 12. So what you do is you put the real parts together and you put the imaginary parts together. The cosine of 7 pi over 12 can be set equal to 1 minus root 3 over 2 radical 2. And if we simplify that, we get this. Sine of 7 pi over 12, so that with the imaginary coefficient, same thing as here. So we equate those parts, and we get this. You would have done this kind of problem in pre-calculus using sum and difference formulas, which we're going to talk about on Wednesday, but this is another technique can be used to figure that out.